In this video, I'll use MicroPython and an ESP32 to create a low-cost wireless device with a color touchscreen to test passwords against a REST API database of hacked online accounts. My videos are fast-paced, but there'll be a full write-up on my website. This project was inspired by a video entitled Have You Been Pwned? By a great YouTube channel called Computerphile. In the video, Dr. Mike Pound creates a Python program to securely check if a password has been leaked by hackers. Many big companies have been compromised. Yahoo, Dropbox, LinkedIn, Adult Friend Finder, Adobe are just a drop in the bucket of rampant security breaches. Besides credit cards and personal data, user passwords are valuable plunder because many people irresponsibly reuse passwords, which puts all their other accounts at risk. This type of attack is known as credential stuffing and is a very lucrative criminal endeavor. Additionally, many people aren't very original when picking a password. Hackers leak the stolen passwords, and they end up in password dictionaries. A security blogger named Troy Hunt has created a popular website called Have I Been Pwned? It allows you to enter your email or your password to check if they've been leaked. I believe the site is legitimate, however, generally speaking, I think it's poor security to check a password or even an unsalted hash on a website. The web server could be compromised, the traffic could be monitored, or it could just be a malicious site. This could let hackers know your password and IP address. Even if they don't get your password, they might be able to ascertain that you have a weak password. Fortunately, Troy's website provides a free REST API that implements a k-anonymity-based protocol. It allows you to securely check a password without transmitting your password or disclosing to the web server if your password is weak or secure. In addition to the Python program that Dr. Pound created to pull the Have I Been Pwned REST API, his GitHub Repo also currently contains versions in Go, Haskell, PHP, Julia, Perl, PowerShell, Bash, C#, and HTML. I thought it'd be a fun project to port the code to a microprocessor. Therefore, I decided to go with MicroPython and an ESP32. And I already had several older Lowland 32s in my junk bin. These boards also come with a built-in LiPo battery jack and charging circuit, so all I need is a touchscreen. For the display, I chose an ILI 9341 2.8-inch 320 by 240 pixel color LCD with a built-in XPT2046 touchscreen. It's 3.3 volts, so it can easily be powered from an ESP32. Amazon sells the display for around $10 to $15 US. It uses a SPI interface, so it's very easy to connect to the ESP32. The wiring is very straightforward. The touchscreen IRQ or interrupt pin is connected to GPIO 0 on the ESP32. The interrupt goes low whenever the touchscreen is pressed. Unlike CircuitPython, MicroPython supports hardware interrupts, so you can create handlers that fire when the screen is pressed, as opposed to just constantly pulling the screen. The touchscreen DO or data output pin is connected to GPIO 19, which is MISO or master in slave out on the ESP32's hardware vSPI bus. The touchscreen DIN or data in is connected to GPIO 23, which is MOSI master out slave in. The touchscreen CS chip select pin is connected to GPIO 5. The touchscreen CLK or clock pin is connected to GPIO 18, which is the vSPI clock. The SPI interface for the touchscreen and LCD display are broken out into separate pins. Normally I'd daisy chain the two SPI devices on the same bus to save pins, but unfortunately they run at very different speeds. The LCD display can run at over 50 MHz, which is great for fast drawing, but the touch controller generates a lot of errors if you go over 1 MHz. Fortunately, MicroPython exposes two of the ESP32's hardware SPI buses. SPI bus 1 is HSPI, and bus 2 is vSPI. The LCD display clock pin is connected to GPIO 14 on the ESP32, which is the HSPI clock. The LCD display MISO pin is connected to GPIO 13, which is the HSPI MOSI. DC, which selects between data and command mode, is connected to GPIO 4. The reset pin is connected to GPIO 17. The LCD CS pin is connected to GPIO 16. The ground pins on both boards are connected. The 3.3 volt pins on both boards are connected, along with the LCD backlight. Some ILA 9341 boards have the backlight pin connected to a transistor so it can be controlled from a GPIO pin. This is convenient if you want to turn the backlight on and off from code, such as if you wanted to implement a sleep mode. My board didn't come with the transistor, so I just wired it directly to 3.3 volts. I designed a case in SketchUp to hold the display, the ESP32, and a LiPo battery. A slot on the side will hold a stylus like the old Palm Pilot. There are two other openings on the sides for a slide switch and the ESP32's micro USB port. Here's the bottom half of the 3D printed case. I installed 2.5mm threaded brass inserts. The 4 outer ones will hold the case together and retain the display. The 2 inner ones will secure the ESP32 board. I added a small through hole on the bottom so the ESP32's reset button can be pressed when the case is closed using a paper clip. The white stylus fits securely into the round slot. By the way, the stylus came with the ILA9341 display. A small slide switch snaps securely into the case. The switch controls the positive lead from the battery. The red JST connector goes to the battery, and the white JST PH is for the ESP32. The ESP32 will be powered by a 3.7 volt, 750 mAh LiPo battery. It fits snugly between the threaded inserts and plugs into the red JST connector. Off camera, I soldered all the connections between the ESP32 and the ILA9341. I added some hot glue on the ESP32 to secure the wires. I also loaded the MicroPython firmware onto the ESP32. The white JST PH plug fits tightly into the battery jack. 2 2.5mm Torx screws holds the board in place. By the way, old hard drives are a great source for small metric screws to secure PCBs. The ESP32 is positioned so the micro USB jack is accessible when the case is closed. It's probably not necessary, but a small piece of anti-static plastic is placed between the boards just to prevent contact between the boards in case someone presses too hard. The LCD display lines up with the 4 outer screws, and the top of the case snaps securely to the bottom. 4 2.5mm stainless steel socket flathead screws go through the top cover, through the LCD display, and into the brass inserts on the bottom of the case. That takes care of the assembly. Next, a micro USB cable is plugged into the ESP32. The other end of the USB cable is plugged into a Raspberry Pi 4. The Pi will provide REPL access for the ESP32 and help with file management. I find that FTP is the fastest and most convenient way to get files onto the ESP32. Robert H.H. has created a small open source MicroPython FTP server. It's compatible with ESP8266, ESP32, and the Pi board. The GitHub link will be on my site. Click the clone button and copy the address to the clipboard. Then minimize the web browser and open up a blank terminal. CD into the Downloads folder and type git clone and then paste in the address. FTP is appended to the command to shorten the long folder name. ls shows the FTP folder containing the repo. In order to use the FTP server, the ESP32 will need Wi-Fi access. Nano main.py creates a blank Python file. I'll paste in the code to establish a Wi-Fi connection. Main.py automatically runs after the ESP32 boots and will connect to my access point called Rototron. I've already covered the main.py file and FTP access in my previous ESP32 tutorials, and I've demonstrated how to set up the ESP32 and necessary tools such as ESPtool to load the firmware and rshell for REPL and file management. If none of that sounds familiar, I recommend you watch my prior videos too. Ctrl-O saves the file, and Ctrl-X exits Nano. rshell is run to connect to the ESP32 on TTY USB 0. ls/pyboard shows that the ESP32 doesn't contain any files other than the boot file. ls alone shows the contents of the Downloads folder, including the FTP folder and the main.py file. cp main.py/pyboard copies the main.py file to the ESP32. cd FTP switches to the FTP folder. ls shows the FTP file. cp ftppy/pyboard copies the FTP server program to the ESP32. ls/pyboard shows that the FTP Pi and main.py were both successfully copied to the ESP32. REPL enters the MicroPython REPL. Ctrl-D initiates a software boot to ensure the ESP32 is connected to Wi-Fi. Afterwards, import FTP starts the FTP server. Now the file management can be done with an FTP client or an IDE with FTP support. I went ahead and created an open source MicroPython library for the ILI9341 and XBT2046 touchscreen display. The repo contains all the code that will be used in this project. I've switched from the Pi to my main desktop computer. Atom, which is a good open source IDE, is running. I'll open the command palette and select GitHub clone, paste in the link to my ILA9341 library, and put it in a folder called MicroPython ILI9341. The repo is quickly downloaded. The folders and files are visible in the tree view on the left. There are a lot of demos, sample fonts, sample images, and all the code is thoroughly commented. The ILI 9341 MicroPython library is a port of my earlier SSD 1351 OLED display library, which I covered extensively in a previous video. The syntax for drawing, shapes, fonts, sprites, and images is the same, so I'm not going to go over it again. Instead, I'll focus on what's new, specifically the pwned password API search code, the touchscreen driver, and the touchscreen keyboard. I'll open touchkeyboard.py. There's a single class called touchKeyboard, which implements a touchscreen keyboard for the ILI 9341 display. Color constants for yellow and green are defined. A tuple called keys is instantiated, and it's comprised of nested tuples for each keyboard screen and corresponding rows. The first screen is for lowercase letters, the second is for uppercase, the third is numbers and symbols, and the fourth is numbers and additional symbols. The touchKeyboard init method takes a display and a font. The display is an ILI 9341 LCD class, and the font is XGLCD format. The pass parameters are stored to instance variables. KBScreen sets the default keyboard screen to 0, which is lowercase letters. KBText will store the text that's typed on the keyboard. The loadKeyboard method is called. It shows the default lowercase letters screen on the LCD. A waiting flag designates if the program is waiting for a press to continue. Locked will be used to lock the keyboard to prevent further input. The clearText method will just wipe any typed text displayed above the keyboard using a black rectangle, and KBText is set to an empty string. The handle keyPress method will be passed to the touchscreen interrupt handler. It receives the XY coordinates of where the touchscreen was pressed. An optional debug parameter can be used to calibrate the touch interface. The method returns true if the search key is pressed. If the keyboard is locked, the method ignores any presses and returns. If the keyboard is waiting for user input to proceed, then any press will allow the program to continue. Any prompts displayed above the keyboard are cleared, and the flag is reset. The display is used in landscape mode, so the XY coordinates are swapped. In debug mode, every screen press will draw a small circle in green, corresponding to the XY coordinates. The keys are divided into rows and columns. The row and column of the screen press are determined from the XY coordinates. The pressed key is retrieved from the keys tuple based on the current keyboard and the row in the column. A few special keys are handled. \T or \F toggles between the lower and upper case or flips the symbol sets respectively. XORing the current screen by 1 switches between the lowercase screen 0 and the uppercase screen 1, or between the first symbol screen 2 and the second symbol screen 3. Load keyboard then displays the selected screen. \A switches from the numeric screens to the alphabetical screen 0, and \N switches from the alphabetical to the numeric screen 2. \B implements backspace. A letter is truncated from the keyboard text. The margin is calculated using the font measure text method. Then the display fill vrect method draws a vertical rectangle in black to clear the erased letter. \R is the return key, which if there's any typed text will fire the search algorithm by returning true. Otherwise, the margin for the next character is calculated using measure text. The press key is a letter, number, or symbol, so it's appended to the keyboard text. Then display draw letter writes the key above the keyboard in yellow. The method returns false, so the program will wait for the next key press. Load keyboard uses display draw image to draw the different keyboard screens to the display. There are raw bitmaps in the images folder for each of the 4 screens. The show message method is used to display a message in the pass color to the user above the keyboard. Any existing text is cleared. The length of the message is calculated using measured text. The margin is calculated so the message will be centered horizontally on the screen. Display draw text displays the message in the specified color. Next, let's take a look at the XPT2046 touchscreen module. There's a single class called touch. Constants are defined for all the XPT2046 command bytes, such as getX and getY, to get the XY positions of a screen press. There's also pressure, temperature, battery, and auxiliary input. The init method takes a SPI bus, a chip select pin, an int pin, which is the ESP32 GPIO pin connected to the touchscreen interrupt pin. InHandler is a method that will be called when the interrupt fires. The width and height of the touchscreen in pixels, X-min and max and Y-min and max, are set to calibrate the display. These numbers can be tweaked for better accuracy. Parameters are stored to instance variables. The chip select GPIO pin is initialized as an output and set high. RxBuff and TXBuff are buffers to receive and transmit data on a SPI bus. Width and height are stored. The minimum and maximum XY values are stored, and multipliers and adders are calculated to normalize screen coordinates. The interrupt pin is stored and then initialized as an input. The interrupt handler is stored, the touchscreen is unlocked, and the interrupt handler is defined. The handler will be triggered on either a falling voltage or a rising voltage, and we'll call the intPress method below. The getTouch method isn't used in this project. It affords manually polling the touchscreen to see if it's pressed. It also takes multiple samples along with a deviation analysis, which should improve accuracy. The method isn't necessary because this project is interrupt driven. The intPress method is called when the screen is pressed. The value of the IRQ pin is passed. If the interrupt pin is low and the interrupt is not locked, then the INLOCKED flag is toggled to ensure only one press can fire at a time. A variable called buff stores results from the raw touch method below. This method gets the XY coordinates of the press that fired the interrupt. This is done by calling sendCommand, which sends commands to the XPT2046 chip and passing in the getX and getY command bytes. If the XY values are within range, the buffer is returned. The sendCommand method receives the command byte, which is placed into the transmit buffer. Chip select is pulled low, and SPI write read into sends the command and simultaneously returns the result. Chip select is pulled high, the results are converted to an integer and returned. The buff variable should now hold the XY coordinates of the touchscreen press. The handler checks that the buffer is not empty, and then normalize is called. The normalize method converts the 12-bit resolution touchscreen coordinates to the LCD display XY pixel coordinates using the corresponding multiplier and adder. The normalized coordinates are returned. The touch keyboard interrupt handler is then called and passed the XY pixel coordinates. A 100 millisecond sleep is used to debounce the screen press. Else, if the interrupt is high and the interrupt is locked, this indicates the release of pressure on the touchscreen. Sleep is used again to debounce the release, then the interrupt lock is released. That's it for the touchscreen driver. Finally, let's look at pwned-search.py. From machine, import pin and SPI to interact with the ESP32 GPIO pins and SPI buses. From #lib, import SHA-1, which is a cryptographic hash function. From ubin ASCII, import hexlify, which is used for hexadecimal conversions. From Urequests2, import get, which will be used to pull the REST API. MicroPython has a built-in Urequest library, but I ran into memory allocation errors while using it, so I switched to a fork by Borrill. It solved the memory errors. Chris is the same author who created the INI219 library that I used in my Raspberry Pi power measurement tutorial. From network, station interface, and WLAN are imported. The Wi-Fi connection is handled by main.py, but we still need to monitor that the connection hasn't dropped. GC is imported to optimize garbage collection. From XPT2046, touch is imported. This is the touchscreen driver that I demonstrated earlier. From ILI9341, import display and color565. Display is the class to control the LCD display. Color565 is used to select RGB 565 colors for drawing to the display. From XGLCD font, import XGLCD font. This class lets you use fonts to draw text on the display. From touch keyboard, import touch keyboard. This is the touchscreen keyboard code that I demonstrated earlier. And from time, import sleep. There's a single class called pwned-lookup. The init method takes a SPI bus for an LCD and a second SPI bus for a touchscreen. There are parameters for DC, chip select for the first bus, reset, chip select for the second bus, and screen rotation. Some ILI9341 displays have the touchscreen overlay applied in different orientations. Therefore, to ensure the XY coordinates of the touchscreen line up with the pixel coordinates of the LCD display, it might be necessary to adjust the display rotation by 180 degrees. In this case, either 90 degrees or 270 degrees. An LCD display is instantiated and passed the first SPI bus, DC, CS, reset, screen width and height, and rotation. Unispace, an XG LCD font, is loaded from the fonts directory on the ESP32. The font character dimensions are 12 by 24 pixels. A touch keyboard is defined and passed the LCD display and the Unispace font. A touchscreen is defined and passed the second SPI bus, chip select 2, the interrupt pin, and a handler method called touchscreen press, which fires when the interrupt triggers. The method is defined below. The init section concludes by storing the Wi-Fi. The only other method is called lookup. It takes a password and returns the number of times the password was found in the online pwned database. A variable called SHA-1 is set to the SHA-1 message digest of the UTF-8 encoded password. This is a hash function which returns 20 bytes because SHA-1 is 160-bit. SHA-1 is then converted using hexlify and decoded to a 40-digit hexadecimal string in uppercase UTF-8 format. The string is split into two pieces. Head is the first 5 digits, and tail is the remaining 35 digits. SHA-1 is no longer considered a secure way to hash passwords, but it doesn't really matter in this scenario because of the k-anonymity model. The Have I Been Pwned REST API is only sent the first 5 digits of the hash, which is relatively innocuous. The REST API will then return all tails that match the head and their corresponding hit counts. Therefore, the REST API doesn't see our password or know if it's compromised. Before calling the online REST API, WLAN is connected, confirms a valid Wi-Fi connection. Otherwise, an I/O error is thrown. A variable called hits will track how many times a password appears in the pwned database. gccollect initializes garbage collection to maximize memory before calling the REST API, which can be memory intensive. It's probably not necessary now because I switched from the built-in MicroPython requests library to Chris's more efficient forked version. With-get calls the pwned passwords API. The route is set to range and provided with the head containing the first 5 bytes of our hashed password. It returns a response. The program loops through each line in the response. A key component of the k-anonymity obfuscation is a large response of around 500 lines. The iterlines method allows processing of one line at a time to save memory. The built-in MicroPython requests library currently doesn't have this functionality. Instead, it loads the entire response into memory, which I found resulted in allocation errors. This is probably exacerbated because I'm using an ESP32 board with an older WROOM32 chip. The newer WRover chips add several megabytes of PSRAM memory. Each line will contain a 35-digit tail and the hit count separated by a colon. A variable L is set to the decoded line based on the response encoding and is split on the colon into tail and hit count. A password match is indicated if a returned tail equals the tail from the original hash. Notice a key advantage of the k-anonymity model is that the actual password matching occurs on your local machine, as opposed to on the remote web server. If there's a match, then hits is set to the returned hit count, and break exits the loop. gccollect cleans up again, and the hits are returned. The touchscreen press method is fired when the touchscreen is pressed. It receives the XY coordinates in screen pixels of the touch. It calls the touch keyboard handle key press method and passes the XY coordinates. If true is returned, it indicates the keyboard search key was pressed. The keyboard is locked to prevent any additional input until the search is complete. A variable pwd is set to the password typed on the keyboard. A message is displayed on the LCD above the keyboard indicating a search in progress. The text is blue. A try statement will catch any errors. A variable hit is returned from the lookup method, which is passed the password to lookup. If there are hits, then the password was found in the online database. A message is constructed to show the number of password hits, and keyboard show message displays the results on the LCD in red. Otherwise, the password was not found, which show message indicates in green. If there are any exceptions, then the first 22 characters of the error is displayed in white. Keyboard waiting is set to true, which suspends the program until the user taps the screen. The search is complete, so the keyboard is unlocked. The program's main method defines the SPI bus for the LCD and sets the speed to 51.2 MHz on the HSPI bus. Then the SPI bus for the touchscreen controller is defined and sets the speed to 1 MHz on the vSPI bus. Pwn lookup is called and passed the two buses. Since the program is interrupt driven, an infinite while loop will be used to keep the program running. Okay, I'll close the code. I installed an add-in package called Remote FTP, which is an FTP client. Click Remote FTP, toggle to show the Remote tab, switch to the tab, and click Connect. This connects to the FTP server running on the ESP32. The three existing files, boot.py, ftp.py, and main.py are visible. I'll click the Projects tab to switch back to the project folder. Expand the Fonts directory, right-click on the Unispace font, and upload it via FTP to the ESP32. Next, expand the Images folder, and right-click and upload the numbered KB images. These are the raw bitmap images for each of the 4 touch keyboard screens. Then upload the ILI9341 LCD display driver to the ESP32. Upload the pwned-search code to the ESP32. Upload the touch keyboard library, the Urequests2 library, the XGLCD font library, and the XPT2046 touchscreen controller library. Click on the Remote tab to switch back to the ESP32. It now contains all the files that were just uploaded. Okay, that takes care of all the code. Switching back to our shell on the Pi, Control-C stops the FTP server on the ESP32. Control-X exits the REPL. Control-D exits our shell. Now let's make sure the pwned-search program starts automatically. I run our shell again, but this time add tac-e nano. This allows editing files directly on the ESP32. Edit/pyboard/main.py opens the main.py file on the ESP32 for editing. Since the main.py file runs automatically at boot, import pwned-search is appended so it'll automatically run after the Wi-Fi is connected. By the way, in case you're concerned, the SSID and Wi-Fi password above are not my real SSID or password. It's just for the video. Control-O saves the changes, and Control-X exits the editor. The touch keyboard is displayed on the LCD. I'll go ahead and unplug the USB from the Pi. Now the device is running on the battery. Toggling upper and lower case works. Switch to numbers and symbols, and the second screen of symbols. The letters are working, and the backspace works. Okay, let's try a really bad password. The program is now searching the online database. And there are 3.7 million hits. Some people erroneously think that substituting symbols for letters or leet speak is a good password strategy, but it's too common and easily defeated with rule-based attacks. Better, but still 181 hits. Let's try a 10-digit mixed case with symbols and numbers. I'll use my finger to hit the search this time. You don't have to use the stylus. Still not good enough. The password was leaked once. One password strategy is to select 4 uncommon, unrelated words. It's easy to remember, and yet difficult to crack as long as the words are obscure. It doesn't hurt to throw in some unnecessary punctuation. A few misspellings would be good too. Okay, password not found. That would have been a good one, although not anymore. Please don't use any passwords shown on YouTube. I hope you enjoyed this project. You can support this channel by leaving a like, sharing, and subscribing. Thanks for watching.